Hello, welcome back to a new video. In this two-part series, we're going to be going over the books that are on my bookshelf. Specifically, we're going to be going over the physics and mathematics books. These math and physics books are a part of my journey in researching physics and mathematics, but I also use online resources for my study as well. In this first part, we're going to go over the mathematics section of my bookshelf. So this is the whole bookshelf. I have a couple other books not shown on the shelf. On the bottom section is the mathematics part. And they kind of mix match because I can't fit them all on the shelves, symmetrically, but we got it close enough here. In the second part here, we have the physics books. And then I just have the other sciences at the very top. So we're going to go over this red section here. This mathematics section is further split up into 10 subsections. Section 1 is mathematical methods, reference guides, and tables. Section 2 is elementary mathematics. Section 3 is college algebra, geometry, trigonometry, and pre-calculus. Section 4 is logic, discrete mathematics, proofs, and special topics. Number 5 is elementary real and complex analysis. Section 6 covers linear algebra. Section 7 covers ordinary and partial differential equations. Section 8 covers probability, variational calculus, topology, functional analysis, and integral equations. Section 9 covers abstract algebra, Lie groups, Lie algebras, geometric algebras, and vertex operator algebras. Section 10 covers tensor calculus, differential geometry, gauge theory, and quantum Riemannian geometry. So let's start with Section 1. So starting out the gate, we have this mathematical methods by these very highly respected Russian mathematicians. And this gives just a general overview of arithmetic, elementary algebra, all the way up to group theory, functional analysis, differential equations, you name it, all of the main fields of mathematics are covered. This is another decent book by Riley, Hobson, and Bentz, a very famous book covering the mathematical methods for physics and engineering. If you want to read these little prompts at the bottom here, feel free to do so by pausing the video. This is a decent book that a lot of people don't know about. It just gives a bunch of tables of, integral tables, derivative tables, Chebyshev polynomials, different things regarding Fourier transforms, Laplace transforms. Again, it's one of those, name a field of math, and it probably has something related to that inside of here. A very good reference manual for sure. Starting off with elementary mathematics, we have Math 8, a reference guide from the K-12 Summit curriculum. And this is just a basic reference manual. There's no actual practice problems or anything to get into here. It's a good reference guide. This, I would say, is an even better reference guide because this gives you a bunch of practice problems to work with as well. I would say this one gets a little bit deeper into the problems that come up in elementary mathematics as well. So starting off here at level 3 is college algebra. This gives a whole lot of examples and practice problems covering a whole range of pre-calculus based topics essentially. So this is everything from geometry, trigonometry, algebra 1 and 2 in high school, and then a little bit more added on to that. That's essentially what this is. Now we have geometry. We have a lot of Shams outlines here, but we're going to be getting away from these eventually once we get into more advanced topics of mathematics. So this one just gives you the basic analytic geometry that you learn in high school and college algebra, essentially. Which is a good introduction towards trigonometry. Again, these Shams outlines, there's not a lot to say about these. They're just really, really good top-tier reference manuals, essentially, for whatever fields of math that they cover usually. You really can't go wrong here. This pre-calculus kind of takes this college algebra idea and just, again, kind of just takes that to the next level to really prepare you for college algebra, as far as like what's needed for introductory calculus, essentially. And a lot of this stuff, since this goes into a little bit of the stuff needed in linear algebra, you can go into vector calculus from this as well. So now in section 4, we're going to move up into some more interesting topics before we get into actual true calculus on its own. So here we have a concise introduction to logic by Hurley and Watson. This is a decent college level textbook on formal and informal logic, and there's a lot of mathematics shown throughout here, and so it's a good way to really get into the mode of thinking mathematically and thinking logically and rationally about the world. And then it finishes it off by helping you distinguish between science and superstition, something that's really missing in our world these days, unfortunately. And so I throw this into the mathematical section. It's a critical book to have in your mathematics collection. And we have another Shams outlines of discrete mathematics. This goes over all kinds of fields of mathematics, starting from set theory and then going over into languages and grammars to ordered sets, lattices, Boolean algebras. Of course, your matrix algebra, operations, matrix algebras, to your groups, subgroups, and homomorphisms of groups, and rings, and fields, all kinds of interesting things that come up in more advanced mathematical topics. But before getting into all that, of course, it still covers all these cool things like permutation, combinatorics, and propositional calculus, and algorithms. This one's really an interesting book to just kind of, it's kind of dip your toe into the water of all these different fields of mathematics that don't show up in a normal, pass through common mathematics. The same is true for this book on proofs, because this covers proof theory under multiple fields. Again, you can pause the video if you want to read more about what's actually in the contents of these books here. This is an interesting book, and it goes a little bit from basic algebra to integral calculus, so it helps to know a bit of calculus too before getting into this book here. The same would be true of the prior book over proofs. This is more of a this is not really mathematical, it's more of a conceptual book covering many different fields of math that involve higher dimensions and then applications in physics as well. And now we're getting into calculus and moving up from there. So usually calculus is a point where people are saying you're getting into intermediate mathematics. So now we have this classic by Morris Klein called Calculus. Now I put this first because this is an easier introduction to calculus than a lot of textbooks, so it's a good way to learn the concepts of it and then also learn the mathematics itself over more basic functions. And this will take you up to multivariable calculus, but not vector calculus. So keep that in mind before buying this book if you want to cover all the way up to calculus 3 and in some cases calculus 4, depending on what region of the world you're in. This book here is not nearly as fun, quote-unquote fun, to read, but it is a very good overview of calculus 1, 2, and 3. So this covers vector calculus as well, and then gives a decent little introduction to differential equations to finish it off. So yeah, this starts from the very basics all the way up to what you would learn in a vector calculus course. This is the same author that wrote the book on mathematical paradoxes I just showed you a while back. But this one's on advanced calculus. So we're talking about starting off with L'Hopital's rule out the gate, and then Riemann and Lebesgue integrals to Feynman's method of integration using, it's kind of like the Leibniz rule method, or where you can use like, you have an integral and you can take a derivative of it and have a t substitution with that, and you create this differential equation, and you turn that into an algebraic equation and solve it, and then you come back to the original form, and then that solves the problem for you. That's Feynman's method. Very useful for a lot of different integrals, some of which are non-elementary and others of which come up in physics a lot. So Feynman's method is very important, and this is one of the few books out there that actually covers that method. So that one's really interesting. It goes further into the stuff that you would see in Calculus 2 and but at a more advanced level, covering the different series, telescoping series, your different tests, Dirichlet's test up to that, the interchangeability of summation with integration, gamma function, polygamma functions, beta functions, Riemann zeta functions, and then applications in physics and chemistry. Very interesting book, highly recommended. If you're getting into real analysis, this is a good book to get into because it's not nearly as tough as a lot of other introductory real analysis textbooks. So this was one of the few of what I would consider an actual true introductory real analysis textbooks. Sauchute's book on elementary complex analysis, I can say the same for it as well. So you're going to be learning, Cauchy's theorem, the fundamental theorem of complex analysis, the Cauchy-Riemann equations, what complex analyticity is, or in other words, what it means to have a holomorphic function set, the residue calculus, which covers Cauchy's residue theorem, and all kinds of interesting things here that are critical in complex analysis. So starting off, we have the Shams outlines of linear algebra. This covers a wide range of information. It probably isn't good for this to be your first book to learn linear algebra from, but it's a good substitute to a textbook, and if you already understand the basics of linear algebra, this is an extremely good reference manual. And for people that are already into more advanced algebra, this is a good refresher. And now we have the classic by Halmos, Finite Dimensional Vector Spaces. This book is legendary, and it's just fun to read altogether. Although if you don't already know linear algebra, this might be a bit of an advanced book to go through. Roman's Advanced Linear Algebra. This is another amazing textbook that covers a lot of features of linear algebra that you may not see on a first pass through university. So yeah, this goes into metric spaces, tensor product spaces, exterior product spaces, and tensor and graded algebras, a little bit of affine and projective geometry, factorization of operators, and a little bit of umbral calculus to finish it off. So you're not going to jump into linear algebra 1 and 2 and necessarily get a deep coverage of it in the way that you would with this textbook here. Tenenbaum and Pollard's Ordinary Differential Equations. This is probably one of the best books ever written on differential equations in human history, and I do not say that lightly. We have Introduction to Partial Differential Equations here. Again, getting into more advanced graduate topics here, this is critical for the study of mathematical physics. So we're starting off with graduate level probability theory. This is good for quantum theory and other fields of mathematics as well as physics. And this isn't just introductory probability either, although some would argue it is, because if you already know and expect calculus to be a part of it, this really is an introduction to probability. But a lot of people don't think of probability as inherently being as advanced as this book is, because this goes all the way towards, from Gaussian distributions and then to discrete and continuous time Markov chains, concepts of Brownian motion, Poisson processes from random processes, etc. So it gets into more advanced topics for sure. So this is very much a calculus-based probability, especially once you get into continuous probabilities. Now we have Introduction to the Mathematics of Variation. This is Sochi's textbook on the calculus of variations. So yes, this is your Euler-Lagrange equations, the variational principle, curves of fastest descent, isoparametric problems, different variable boundaries, and variational problems in general. That's what this essentially covers, and of course this is essential for physics. Now we have Krum's Principles of Topology, another legendary book. This covers point set, geometric, differential, and algebraic topology. At least it gives a decent introduction to all of those fields. So yeah, you're going to learn about bounds, finite infinite sets, open closed sets, planes, interiors, closure, boundary, continuity, metrics, and all the spaces that these things form. So you're going to learn about topological spaces, metric spaces, connectedness, compactness, all these things, all the way up to fundamental groups, categories, and even functors. This is a legendary textbook. Famous Russian mathematician Kolmogorov also contributed heavily to this book on functional analysis. So you start off with these ideas from set theory and functional analysis, composing metric spaces and all these things on sets. Linear functionals, you have Fubini's theorem, orthogonalization, L2 spaces, which are types of Hilbert spaces. So this gets into the idea of Hilbert spaces. And even finishes off with an introduction to integral equations with symmetric kernels. So this is a decent book on Lebesgue integration and measure theory as well. And is a good transition towards an actual book on integral equations. This one's by Tricomi. So you're going to learn about the kernels in L2 spaces, Volterra and Friedholm equations, integral equations of those types, Cauchy's principal value problems, Hilbert-Schmidt theorem, eigenvalue problems. So of course, this being integral to functional analysis, you're going to get a lot of multilinear algebra here. You're going to understand, Hilbert transformations and nonlinear equations of Hammerstein type. So again, this is another fairly advanced textbook here. This here is probably one of the best introductory books on modern algebra. It covers it at an undergraduate textbook level. So it'll even get into stuff like Boolean algebras and vector spaces and how this applies to things in linear algebra a bit, but really this covers the elementary aspects of modern algebra. How do we think of algebra in the current times? So you're going to get into things like group theory, fields, these different subgroups, algorithms, Fermat's theorem, Euler's theorem, a little bit about Lagrange's theorem in cryptography, and finite abelian groups and what that even means to have an abelian or non-abelian group. We're going to go into rings, integral domains, fields, ring homomorphisms, etc. And this right here is hands down, in my opinion, the best book ever written on algebra and one of the best textbooks ever written in any fields of science. This is Serge Lang's classical and absolutely legendary graduate level textbook on modern algebra. So yeah, everything covered in the prior book is basically covered in the very first sections of this book. This is a huge book, over 1,000 pages. So the entire other book is like the first part of this book, and then it goes further from there and it just takes off. So once you're done covering the principles of linear vector spaces and Dill spaces and vectors and stuff of that nature, this goes straight into tensor products, tensor algebras, the Witt group, Clifford algebras, de-Rham complex, and introductory homological algebra. This book also serves as a great introduction to abstract linear algebra as well in general. Now I have an introduction to Clifford algebras and spinors. I would say this is one of the better books to start out on, because you're already getting to Clifford algebras, you're already getting into more advanced textbooks out the gate. This is probably one of the easier ones to start out with. So this will go into Grassmann algebras before it goes into Clifford algebras, once it goes over into the idea of contractions and interior products and exterior algebras and products. And so once you're done covering all these ideas about vectors, covectors, and Vault-2 vectors and the operations upon them, it goes further into applications such as conformal transformations, spinors, file spinors, space-time vectors, twistors that are represented as geometric multivectors, spinor classification, and even it covers the supersymmetry algebra. This book here is a good complement for that other book and looks at it from another perspective. That's a great way to describe this book here. This one also goes into interesting things. It covers a lot of the stuff that's in that last book as well, but it also covers things more specific to things like the uncertainty principle of Minkowski space-time, as you would expect, but things also like Hopf vibration, quaternions and split quaternions, Euclidean force space, the Dirac spectral bases, Lie group manifolds, and the Riemannian geometry of the three-sphere. Interesting concepts here from differential geometry get mixed up once you're studying geometric algebra. This is a graduate book on Lie algebras and Lie group representation theory. And it is a pure mathematical textbook once you jump out of the gate with it, but it really quickly tends towards physics applications. So if you're into things like quantum field theory and the standard model of particle physics, nuclear physics, and different aspects of particle physics in general, you're really going to want to pick up this book. The same is especially true, if not more so, for this book here. This is, in my opinion, the best book ever written on geometric algebra. This is by Lassenby and Doran. They are, of course, pioneers in this field. So not only do you learn the basics of geometric algebra and geometric calculus from this book, from the ground up and then some, but it goes into applications from two-spinner calculus to projective conformal, non-Euclidean, and space-time conformal geometries, Grassmann calculus, Lie groups, how it applies to the Euler-Lagrange equations from a geometric algebraic approach, Lagrangian geometric field theory, symmetries in physical gauge theories that are found in electromagnetism, Dirac electromagnetic theory, and gravity. This is a very, very interesting book to read on its own right, but also a very good way to learn this topic from a basic and advanced level. Now we're getting a bit more abstract here. This is something a lot of people probably haven't heard of. But here we have Victor Kac, who covers vertex algebras for beginners. And this Victor Kac was the same Kac that discovered Kac-Moody algebras. So yeah, this starts off with the Whitman axioms of quantum field theory, goes into chiral algebras, holomorphic vertex algebras, current algebras, the Virasoro algebra, then you have your Lie conformal superalgebras, and then all kinds of extensions of vertex superalgebras, including their subalgebras and superconformal variations. So now we have affine, vertex, and W algebras. So I could spend all day talking about what's all covered here, but vertex algebras are a very recent field of mathematics. I don't know of anyone formally studying them until basically really the 90s, to be truthful with you, although it might have been before, but really people giving a name to them and studying them for their own mathematical sake, I don't even know of being a thing until the 90s, and they're still taking off like crazy. Discoveries in these things are happening essentially every single day. And if you're aware of Michael Penn on YouTube, he also contributed to this book. One of his papers appears in this book. Louis Braham's Vector and Tensor Analysis, a classic textbook. This covers vector calculus and introductory tensor algebra and tensor calculus. And then we have Asham's Outlines of Tensor Calculus, which acts as a good supplement to a tensor calculus book or as a good refresher. This one will range from the Einstein summation convention and Kronecker delta function that's typical in an introductory tensor calculus course, and then ends up all the way with the Einstein tensor and tensor fields on manifolds themselves. Sochi's book on introductory differential geometry of space curves and surfaces is a good way to get an overview of the different concepts in differential geometry. But if you want to look further into differential geometry, I recommend this book here. This is a much more rigorous and interesting introduction towards differentiable manifolds and differential geometry as a whole. So if you're a mathematician that wants to be rigorous, or you're a physicist that's wanting to get really serious about it, I would recommend this book over Sochi's book, whereas Sochi's book's a better conceptual overview of differential geometry. If you're wanting to get into advanced differential geometry and see its applications to things like relativity and quantum field theory, you cannot go wrong with this absolutely fantastic and legendary graduate level textbook. So this covers everything that you see in the last books at a very rigorous level, but then goes on towards Hopf fibrations, Lorentz groups, fiber bundles, gauge fields, and a bunch of Lie group theory topics. Then we have Hamilton's mathematical gauge theory. So if you want to sum up differential geometry as it's applied to modern physics, this is the best book to go to, bar none. So you're going to start off with Lie groups and Lie algebras before going into further applications of differential geometry, such as your general and principal fiber bundles, vector bundles, gauge transformations, local curvature 2 forms, covariant derivatives, exterior covariant derivatives to make things more interesting. Then, of course, your Bianchi identities. And this one goes further into Clifford algebras, spin groups, spin covariant derivatives, and of course your twisted spinner and chiral bundles and applications to the standard model. So yes, quite an advanced book, but it's a good overview for physicists and mathematicians. Then we have the last book on the list here. This is Beggs and Majid's Quantum Riemannian Geometry. This is a non-commutative differential geometry. So we want to think about things like quantum metrics, quantum Laplacians, the different quantum exterior algebras and the de Rham complex, and universal enveloping algebras that come out of the study of quantum Riemannian geometry. This will go into quantum principal bundles and the non-commutative Witt enveloping algebra, bimodule quantum Levi-Civita connections, and then it'll go all the way from there to Dirac operators for endomorphism calculi, Chern connections, and even flat and curved quantum spacetime. I would say this is probably the most advanced pure mathematics book that I have in my collection as of right now. And that's all we have for the first part. I hope to see you soon in the second part where we'll go over the physics collection.